Hello, Matt here from chemistrystudent.com. In this video, we're going to look at calculating moles of gases and the ideal gas law. We're going to talk about moles of gases and the ideal gas law, including the assumption of ideal gases, and the link between the pressure of a gas, its volume, and temperature. Before we talk in detail about the ideal gas law and moles, it's essential you are comfortable with the idea of the mole. The mole, as well as other mole-based calculations, have been covered in separate videos. Check the links in the description below. As a quick refresh for this video, however, the mole is a term used to describe 6.022 times 10 to the 23 of something. The value 1 mole refers to is known as Avogadro's constant and comes from the number of atoms in a sample of an element that has the same mass value as the element's relative atomic mass. For example, hydrogen has a relative atomic mass of 1, meaning in 1 grams worth of hydrogen there are 6.022 times 10 to the 23 hydrogen atoms. Carbon has a relative atomic mass of 12, meaning in 12 grams worth of carbon, there are 6.022 times 10 to the 23 carbon atoms. As a result, the moles of a compound or element present in a sample can be calculated by dividing the mass of the compound or element by its molar mass. Balanced equations in chemistry are based on the molar ratios of reactants and products. For example, 2Na plus 2HCl to form 2NaCl plus H2 means 2 moles worth of sodium atoms react with 2 moles worth of HCl molecules to form 2 moles worth of NaCl and 1 moles worth of H2. Recap done? Let's go! In the early 19th century, the Italian scientist Avogadro proposed that equal volumes of gas at the same temperature and pressure contain equal numbers of molecules. In other words, equivalent amounts of different gases have the same volume at the same pressure and temperature. This proposal actually got picked up by scientists many years later and led to the idea of the mole, with the value 1 mole represents being called Avogadro's constant in honor of Avogadro and his idea. Today we know that Avogadro's proposal about gases is pretty much spot on, and we say that 1 mole of any gas occupies the same volume as 1 mole of another gas at the same temperature and pressure. At room temperature, 20 degrees Celsius, and 1 atmosphere of pressure, this volume is 24 decimeters cubed. I say the proposal is pretty much spot on rather than perfectly correct, as we have to make slight assumptions about gases and how they behave in order for it to always hold true. The key assumptions are that in a gas sample, the individual molecules of gas have a negligible volume that can be ignored, and that there is no interaction between molecules other than perfect elastic collisions. In other words, we think of all gas molecules as tiny points in space that are all the same size and are constantly moving around. And when 2 molecules collide, they simply bounce off each other. In reality, these assumptions aren't exactly how gases always behave, and as a result, we describe gases that are following these assumptions as ideal gases. These assumptions can seem a little bit strange when you really think about it. We know, for example, that different types of gas molecule can absolutely have different sizes. Hydrogen molecules, H2 for example, are a lot smaller than butane molecules, C4H10. Surely 1 mole's worth of each should occupy a different volume as a result. Well, if you measured the exact number of molecules in the same volume of each gas, you may find that there are slight differences. The key thing, however, is that these differences would be absolutely tiny and wouldn't ever need to be worried about in the vast majority of chemistry applications. Instead, we assume all molecules have a negligible volume. Effectively, we're saying the size of the individual gas molecules doesn't matter. And compared to the space they occupy when moving around, it really doesn't. If you are watching a football match and the football is changed for one that is marginally bigger by half a centimetre cubed, for example, would you notice and would it have any impact on the volume of space it occupies compared to the whole football pitch? No. We also assume that the molecules in a gas don't ever interact with each other apart from perfect elastic collisions. There are assumed to be no intermolecular forces between the molecules, regardless of how close they get to each other. Meaning if two collide, only kinetic energy gets shared between them, and the combined kinetic energy of both molecules is the same before and after the collision. Kinetic energy here just describes the energy the molecules have as they move. All of these assumptions for ideal gases mean that when thinking about amounts of gas molecules in a sample, we can ignore the gas type being studied. It isn't important what the gas is, only that it is a gas, and this is really useful. The volume occupied by a gas sample is based on the moles of gas present and the temperature and pressure of the gas. The volume occupied by 1 mole of a gas increases with temperature. This is because as a gas is heated up, the kinetic energy of its molecules increases, and as a result, they move faster and spread out more, increasing the volume occupied by the gas. Equally, if the temperature of a gas is decreased, the kinetic energy of its molecules decreases, and as a result, they move slower and spread out less, decreasing the overall volume of the gas. The volume occupied by 1 mole of a gas also decreases if its pressure is increased. This is because there is more force pushing against the molecules of gas, meaning they effectively get forced closer together and they can't spread out as easily, decreasing the overall volume occupied by all the molecules. If the pressure of a gas is decreased, this would cause the volume occupied by it to increase. In this case, there is now less force pushing against the molecules of gas, meaning they can spread out more, increasing the overall volume that they occupy. There are then 3 key things to think about when dealing with the volume occupied by a gas: the moles of gas molecules present, the temperature, and the pressure. How these are linked together is summarized by something called the ideal gas equation or ideal gas law. The ideal gas law shows the connection between temperature, pressure, volume, and moles of a gas, and is written as PV equals nRT, where P is pressure, V is volume, N is moles, T is temperature, and R is something called the universal gas constant. The units for pressure are pascals, PA, the units for volume, meters cubed, and the units for temperature, Kelvin, K. The equation can be rearranged to give moles equals PV divided by RT. From this rearrangement, we can see that if pressure P is increased and everything else stays the same, the value for N, moles, must increase. As in, there are more moles of gas present in the same volume if pressure is increased. Equally, if temperature T is increased and everything else stays the same, N must be smaller, as the value of PV is now being divided by a bigger value, meaning fewer moles of gas in the same volume at a higher temperature. The gas constant R links the temperature of a gas to its energy, and therefore how quickly the molecules present in it are moving. This is also why Kelvin has to be used as a measure of the gas's temperature, rather than degrees Celsius. The connection between temperature and how quickly molecules of gas move is really important, because if you keep decreasing the temperature of a gas to the point where the molecules have no heat energy and no kinetic energy, they can no longer move and won't occupy a measurable volume. We can see this when we decrease the temperature of an ideal gas, as its volume also decreases. If we plot this on a graph with temperature as degrees Celsius, we get a straight line. If we were to follow this straight line and extrapolate it back to the point at which the volume of the gas is 0, The temperature at that point is very close to minus 273 degrees Celsius. This point is considered absolute zero and is theoretical. We can't actually get things quite that cold. At this point, an ideal gas has zero heat energy, meaning its molecules can't move, and this is why it has no volume. As a result, we start a new temperature scale here called the Kelvin scale, and this point is 0 Kelvin, 0 K. This new temperature scale now links the energy of a gas to its temperature properly, unlike degrees Celsius, where 0 degrees Celsius doesn't mean zero amounts of heat energy. Usefully, a change in 1 degree Celsius is the same as a change in 1 Kelvin. 1 Kelvin, however, isn't the same as 1 degree Celsius. From its starting point on the graph, we can see that to convert between degrees Celsius and Kelvin, add 273. 0 Kelvin is the same as minus 273 degrees Celsius, and 0 degrees Celsius is the same as 273 Kelvin. When something's temperature is measured in Kelvin, we describe its temperature as absolute, as the temperature value is going to be directly linked to the amount of thermal energy it has. The temperature of a gas alone doesn't actually tell us how much heat energy it has, however, as that is also dependent on the moles of molecules present. This is where the universal gas constant helps out. The universal gas constant, R, links the energy of a mole's worth of gas molecules to their temperature. Its value is 8.31 and has the units of joules per Kelvin per mole, meaning it shows how much the energy of 1 mole's worth of gas molecules increases by every time their temperature is increased by 1 Kelvin. Increase the temperature of 1 mole of gas molecules by 1 Kelvin and their energy increases by 8.31 joules. By multiplying the temperature of a gas in Kelvin by the universal gas constant, you get the amount of heat energy 1 mole's worth of the gas molecules have, and therefore the amount of kinetic energy they are moving with, which is itself proportional to the volume they occupy. This is why the universal gas constant is included in the ideal gas law. So, to summarize, the ideal gas law shows the link between temperature, pressure, volume, and moles of an ideal gas. PV equals nRT, where P is pressure, V is volume, N is moles, T is temperature, and R is the universal gas constant. The units for pressure are PA, pascals, volume, meter cubed, temperature, Kelvin, and the universal gas constant R links the temperature of a gas to its energy and therefore how quickly the molecules of gas are moving. Ideal gases are a way of modelling gases that assume their molecules have a negligible volume and there is no interaction between them. This means we don't have to worry about the specific type of gas when using the ideal gas equation. If the temperature of a gas is increased, molecules move faster and spread out more, occupying a larger volume. Decrease the temperature of a gas and molecules move slower and spread out less, occupying a smaller volume. If the pressure of a gas is increased, its molecules are forced closer together, occupying a smaller volume. Decrease the pressure of a gas and its molecules spread further apart, occupying a larger volume. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.